Assalamualaikum and welcome to our video presentation of MAT300 project. Before we get started, this is us as the group members.
Applications of first-order linear differential equation problems, mixture problems.
Let's dive into our intriguing concept in mathematics for today. Mixture problem. Mixture problem is an application of linear differential equations that require us to solve the equation based on the concentration of a substance in a tank. Mixture problem also involve combining two or more things and determine some characteristics of either the ingredients or the resulting mixture. Next, these are the formulas for inflow and outflow of mixture of two solutions. First off, inflow rate of the solution is dV over dt, inflow equals to R1 liter per minute. Then, concentration of this inflow solution is dA over dV equals to C1 gram per liter. Lastly, outflow rate of the solution equals to dV over dt, outflow equals to R2 liter per minute. By simplifying all the formulas onto the mixture problem shown, we then form the standard linear differential equation, which is dA over dt plus R2 over Vt times A equals to C1 Cr. Other than that, we can also use linear differential equations to solve mixture problems. The standard form of a linear differential equation is dy over dx plus px times y equals q of x. By using an integrating factor, which is e to the power of the integral of px with respect to x. Multiply the entire equation by the integrating factor, it will become integrating factor times the quantity dy over dx plus p of x times y equals e raised to the integral of px with respect to x times q of x. Now, the left-hand side becomes the derivative with respect to x of the product of e raised to the integral of p of x and y. So we can rewrite it as d over dx of e raised to the integral of px times y equals e raised to the integral of px times q of x. The integral of d over dx of e raised to the integral of px times y with respect to x equals the integral of e raised to the integral of px times q of x with respect to x. Y equals e raised to the negative integral of px times the quantity of the integral of e raised to the integral of px times q of x with respect to x plus c.
So now we are moving on to the problem statement. An application of first-order differential equation which consider a tank holding 2000 liters of fresh water. Starting at T equal to 0, water containing 0.1 kilograms of salt per liter is poured into the tank at the rate of 8 liters per minute. The mixture is kept uniform by stirring and is drained from the tank at the same rate it is filled. Determine when the concentration of the salt in the tank will reach 0.0 kilogram per liter.
Based on the problem statement, imagine this is our tank. The information that we got for the tank is it can hold 2000 liters of fresh water. So 2000 is the volume of the tank. Now for inflow input, since the problem statement says that the salt is poured into the tank at the rate of 8 liters per minute, so our inflow rate is going to be 8 liters per minute. For concentration, it is 0.1 because the water containing 0.1 kilograms of salt per liter. Next, we can calculate Rin by multiplying inflow rate with concentration. Next is outflow input. The outflow rate remains the same since in the problem statement it says that the mixture is drained from the tank at the same rate it is filled. So it's going to be 8 liters per minute. Since the concentration is not in the problem statement, so it's going to be 80 over 2000 because the formula for the concentration is 80 per volume. So our R out is going to be 80 over 250.
So from the video, what we can summarize is the volume of the tank is equal to 2000 and our inflow rate will be 8 liters per minute Also, for the concentration, it will be 0.1 kilogram per liter. From the information that we got, we can calculate our Rin, which is equal to inflow rate times with concentration, and the answer will be 0.8. Next, for outflow input, our outflow rate it is equal to 8 liters per minute. For concentration, it is equal to 80 per 2000. So our Rout is going to be 8 times with 80 per 2000 equal to 80 per 250.
The rate of change of A with respect to T is equal to the difference between Rin and Rout. This can be written as dA over dt equals R sub in minus R sub out. Next, we substitute R in as 0.8 and R out as A of t divided by 250. This gives us the equation dA over dt equals 0.8 minus A of t over 250. By rearranging the terms, we get dA over dt plus A of t divided by 250 equals 0.8. Now, the integrating factor is calculated as e raised to the integral of 1 over 250 with respect to t. This simplifies to e to the power of t over 250. E to the power of t over 250 multiplied by the quantity dA over dt plus A of t divided by 250 equals 0.8 times e to the power of t over 250. On the left hand side, this expression represents the derivative of the product of e to the power of t over 250 and A of t. So we can rewrite it as the derivative of e to the power of t over 250 times A of t equals 0.8 times e to the power of t over 250. Now we integrate both sides with respect to t. On the left hand side, the integral of derivative simplifies to e to the power of t over 250 times A of t. On the right hand side, the integral of 0.8 times e to the power of t over 250 is 0.8 times e to the power of t over 250 plus a constant c. This results in e to the power of t over 250 times A of t equals 0.8 times e to the power of t over 250 plus c. Finally, to isolate A of t, divide both sides by e to the power of t over 250. This gives us A of t equals 200 plus c times e to the power of negative t over 250.
Next, we will continue to find the value of c. Since the question had mentioned that it starts at t equal to 0, therefore we will write it as A of 0 equal to 0. After substitute the information into the equation of A, we will get the value of c, which is negative 200. Next, we will substitute A of t into c of t. Then, multiply both sides by 2000 to eliminate the denominator. And after that, simplify the equation. Now, we will get 120 equal to 200 e power of negative 1 over 250t. Next, divide both sides with 200, which later we also need to eliminate the exponential term by applying the ln to both sides of the equation and solve it to find the value of t. Lastly, we will get the answer, which it will take approximately 1 to 7.7 minutes for the concentration to reach 0.04 kg per liter. Conclusion. In this video, we demonstrate a practical application of first-order ordinary differential equation through the solution of a tank mixing problem. When t equal to 0, we can find the concentration of salt in the tank will reach 0.0 kg per liter after approximately 1 to 7.7 minutes. The result demonstrates how first-order linear differential equation can be used to model and predict changes in concentration in dynamic systems, such as mixtures in tanks with inflow and outflow processes. So, here is our references that we use in our video presentation. That's the end of our presentation. Thank you for watching.